Should I ask individual students or just throw the question generally? Or you all like general questions? Is it possible to have motion in the absence of a force? Explain.
Would that mean like the net force is 0?
When the net force is 0?
Yes.
Yes. Okay. In the absence of a net force, you're still, it can be moving with a constant velocity, right? When your car is going on cruise control, what's the net force on the car? 0. Because the upward and downward forces are balanced. Forward force is the driving force, which is provided by? What is providing the forward force? The engine? What moves your car forward?
Oh, the ground pushing the ground.
Friction. Friction is the one which is really necessary. You can have the best engine. So the car is not going to go anywhere without the real grip. Okay, so you need friction. So what drives your car forward is friction. So there is a forward force, which is the friction force. That is what takes the car forward. What is the backward force? Also friction, but the air resistance mainly, right? So you can have driving force, air resistance, normal force, weight, all balanced. If an object is at rest, can you conclude that no external forces are acting on it? No? What's the explanation? James?
Balance.
Say it again?
They're balance forces. It appears that nothing's happening.
Yeah. So you can have thousands of forces, but as long as they're balanced, then you can have the object at rest or even moving with a constant velocity. If an object is thrown into the air, stops at the highest point in its path, is it in equilibrium at that point?
No.
An object thrown into the air stops at the highest point in its path. Is it in equilibrium at that highest point?
No, because gravity's still going on.
There's only one force acting on it, which is gravity. So which means it is not net force is equal to 0, right? So since gravity is acting on it, even though it is at rest, there is a net force. You get it? At that moment. That's what brings it down, actually. But at that moment, it is not moving, but there is a net force still acting on it. Okay? Let me know if you have any other questions as I'm reading these things. Yeah.
So on the car example, like where you said friction was what was driving forward, how exactly does that work? I'm kind of confused. Like I understand friction in the opposite direction.
So what exactly is happening when the car is moving forward is like the wheel is gripping the ground. Okay, the wheel is gripping the ground. Now, when the wheel is attempting to turn, but the grip is not letting it go, what happens is the axle starts moving forward.
Okay, that's what applies forward.
That is what is taking it forward. It's because the wheel is, suspended by the axle, right? So when the wheel is forced to turn, but it is touching the ground, so there's no chance of the wheel slipping because the grip is more. So then the only other consequence is go forward. That's exactly what we do when we walk. What makes you walk forward? Friction. So when you're walking forward, there's friction acting forward. Without that friction, you'll keep slipping and staying in the same place. So we are gripping the ground and dragging the ground backward. Unfortunately, the ground cannot go backward. So you are weak, so we go forward. Okay? You must have seen those instances when in a circus and all that, there will be a big globe and there will be a tiger standing on top of the globe and walking on top. So what is the tiger doing? It is just walking on the top and the globe starts rotating and the tiger is always at the same spot. Have you seen that? Tiger is always the same spot, but this globe is rotating, so it goes like this. Now we are also like little tigers sitting on this big globe, the real globe. And what are we trying to do? Push the globe backward because you can go forward. You're sitting on top of the globe, the earth, and you're trying to drag the ground backward so you can advance forward. But then we fail miserably. And as a consequence, you end up going forward. You know? So yes. So that's the definition of walking. Man, in an attempt to move the earth backward, fails, and as a consequence moves forward. Yes, Jim.
When your car is driving, that's static friction, not.
It is static friction.
And when it like
Good question.
oversteers or drifts, it's
Yeah.
like
Only when it drifts, it is actually kinetic friction. Otherwise, it is a static friction because the wheel is making a firm contact with the ground at each and every spot. So as the wheel spins, it makes new contacts and leaves the old one out. You get it? So when the wheel is spinning, when the wheel spins, all right. So when the wheel spins, you can see what's happening there. The contact is right there, and it makes a contact, and as it starts moving forward, so this is the wheel. See, I'm trying to drag the wheel back. I'm trying to drag the wheel like this. I'm trying to scoot the wheel, but because of the grip, the wheel starts spinning, and I'm moving forward. So it is basically the ground. So the friction that is offered by the ground is what actually takes. That's what takes it. Yes.
So like going back to Andrew's question about like how friction moves it forward, like on not the last mastering assignment, but the one before that, they had like the question about the runner and like you kind of like said it when like walking, but like I know like one of the answers was that the ground was moving the runner forward. But is it actually just like a friction made from the?
It is a friction from the contact. Yes.
Okay.
It is not just the ground. The ground is offering two forces. When you're running, the ground is offering two forces. One force, so that's your leg, kind of. So when you're actually making contact on the ground, as you step on the ground and then walk, there are two forces. One is a frictional force forward, and then there's a contact force, the normal force and frictional force. Where's the resultant of this? That way. That's why you kind of leap upward. Right? When you run, what actually is making you take off is this force. Because the resultant force is in that direction. Yeah.
So would we get more friction with or without our shoes on in running?
Say that once again.
Like if we were bare feet or with shoes, which would we get more friction with?
It depends on what kind of shoes and depends on what surface you're running. It all depends now. If you're talking about the normal grounds, and I mean normal, I don't know, you say. I think if we are running on a sand, bare feet will be better or shoe will be better. I don't know. Bare feet is better on sand?
Yeah, because you can do.
Because probably you can dig in and then like push the whole thing back. Yeah, probably that makes a difference. And if you're on a turf, maybe, proper shoes. Yeah, the shoe makes a big difference. In terms of running and speed and stuff like that, shoe makes a big difference. The spikes will add to the grip. Okay. Yeah, any other questions? Question. So what takes a plane forward? How is a plane going forward? What is the force that takes a plane forward? Yeah. Anyone?
Doesn't it like it sucks the air and then pushes it out behind it and do it forward?
So what is taking the plane forward is my question. Yes. Fluid friction actually is supposed to oppose it. Fluid friction will oppose it. Yeah.
Is it propulsion? Like when it's propelling,
So what is propulsion?
it's displacement.
Okay. Let's take a different example. When you swim, what force makes you go forward when you swim? What is pushing you?
Your hand.
You pull the water.
Are you pushing the water or water pushing you? Both. You are initiating the process by pushing the water backward.
Pairs of forces.
When you push the water backward with whatever force, the water applies an equal and opposite force back on your hands. And that is what takes you forward. So the more you apply on the water, the more it will help you to go forward. You get it? So what is actually making you swim forward is water. Same thing with the plane. What is actually happening in the plane? The propellers are actually spinning, and like you said, the suction thing, yes, but what is actually happening is it collects the air and pushes the air backward.
The air is pushing it.
So the air is pushing it forward. Simple. So what takes the airplane forward is air. Okay. Rocket. What takes the rocket up? What creates an acceleration on the rocket upward? What is happening in the rocket is it burns the fuel, the gases, and it takes the chunk of gases which are burned and expels it, throws it out. So when the gases are given a big push downward, what do the gases do to the rocket? Push it upward. And if that push upward is greater than the weight, then it's going to accelerate. Right? You get it? So which law of physics is that? The third law. So third law is what deals with all those kind of things. Now another example, imagine you are on a totally frictionless surface. Imagine you are on a totally frictionless surface, like you know the air hockey table. That sort of, okay, no friction at all, and you're standing there. And if I'm telling you, can you go forward? What will you do? Practically, think about practically too. Your goal is to go there. You want to go to that wall, and there's absolutely no friction to help you. Yes.
Throw something behind you.
Huh?
Throw something behind you.
Throw your shirt. Take your shirt off. Bundle it up and throw it behind you. So as soon as you throw the shirt behind you, what will the shirt do to you? Push you forward. And if it is totally frictionless, you can just blow air. Like, and here you go. Like a rocket. All you need to do is just blow air, and then that is enough, because when you blow air, you are pushing the air forward. So what does the air do? Immediately push you backward. And that is enough to keep you drifting, because now somebody has to stop you, otherwise you won't stop. You know? So yes, all you do is push an object, and the object will push back on you immediately. So frictionless surface, that's the only way to kind of advance. You have to throw something. Okay? If you are standing on a log of wood, and the log of wood is on water. So now there's a log of wood, and there's water. If you start walking forward on the log of wood goes backward. Can you tell me what forces are making you go forward and the log go backward? Yes?
Fluid friction and then static friction or solid friction with your feet on the log.
So what is making you go forward? Tell me that answer once. Yeah, just that answer. Yes, Adam?
When you push on the log, right?
Log.
Yeah.
Okay.
When you push on that, it makes you go forward.
So what is the force that's making you go forward? What force?
You know,
I want, yeah, friction, yes. From where to where?
from your foot to the log. Down.
You are the object, and you're going forward. So there must be force acting on you to take you forward. Yeah, think about it. Yes,
Isn't it the solid friction from the log?
from the log on your feet. Yeah, the log applies a frictional force on your feet, and that's what takes you forward. Now, what is the force that takes a log backward? Yeah,
The force you apply to the log.
what force?
Solid force.
It's a friction again.
Solid friction.
It's a Newton's third law pair. When the log applied a force on you, you are applying a force on the log. Simple, right? When the log, when I grip and drag, the table is applying a force on my hands forward. I'm applying a force on the table backward. Make sense? So those are Newton's third law pair. And so the answer goes like that. the force of gravity on a 2 kilogram rock is twice as great as that on a 1 kilogram rock. True or false? The force of gravity on a 2 kilogram rock is twice as great as that on a 1 kilogram rock. Again, I read it once again. The force of gravity on a 2 kilogram rock is twice as great as that on a 1 kilogram rock. True. Force of gravity is mass times gravity, right?
Yeah.
That's true. Why then doesn't the heavier rock fall faster? Huh? Why then the heavier one is not going faster?
Air's acceleration is the same.
The acceleration is the same, 9.8, negative 9.8. The force depends on the mass. Acceleration is totally different thing. So in other words, all the objects are going to fall with the same acceleration, be it a sumo wrestler or Laurel. You know Laurel, right? Laurel and Hardy? No? Okay. You look up Laurel and Hardy. They were, characters. Okay, wait. Charlie Chaplin?
Yeah.
Okay, you know that. Okay. Before that was Laurel and Hardy. So a lot of Laurel and Hardy movies. I've seen a lot of Laurel and Hardy movies. Interesting. I mean, they're the comedians basically. Hardy is a hard guy, fat, and the Laurel is skinny. So they're always like playing around with each other, and that's basically what it is. But it's just funny. Anyway, so that's why I said Laurel. So imagine a sumo wrestler and a skinny person falls from the top. They both will accelerate with the same acceleration, at least initially. Okay. So if I drop a feather and a coin from the top of a building, what will be the initial acceleration of the feather and the coin? It will be 9.8. But what happens after some time? The air resistance start affecting the feather a lot more than the other one. Therefore, the feather will reach the terminal speed very soon, and it will start coming down very slowly. Whereas a coin will come down with a much faster terminal speed because the air resistance is very small on it. You get it? Yeah.
This is kind of a silly question, but in the case, I've heard this before, if you throw a penny off the Empire State Building, would it pick up enough speed to severely injure someone?
Nah.
Okay.
Because of the air resistance. Thank God for that. The air resistance is something that actually stops a lot of those fast moving things. But yeah, it will be fast enough, but it won't be like, it will reach terminal speed at some distance. Of the other question. Yeah. I don't have the proper setup, otherwise I could have demonstrated it. But it's a cylinder. It's a cylinder which has a coin and a feather inside. Okay? Cylinder which has got a coin and feather inside. So if you take the cylinder, the coin and feather are right there. And if you just flip the cylinder like that, the coin comes down rather quick and the feather comes down like slow, right? And then we connect to a vacuum pump. We connect it to a vacuum pump and evacuate this cylinder, remove the air from it. So once the air is literally taken out, you seal it again. Now the coin and feather are here. Just flip it and both will come down together. It's kind of unbelievable, but it's true. It just comes down together because there's no air resistance now. So both of them will suffer the same acceleration. All right, so they both come together. So you can just imagine like there's a coin and a feather, and when you turn it around, the coin and feather just fall parallel together. because there's no air resistance. And the moment air is opened up, then it is free to. All right. Questions? Yes.
Is that assuming that like the feather and the coin weigh the same?
Doesn't matter.
It doesn't matter.
The mass doesn't matter because the acceleration does not depend on the mass. Acceleration does not depend on the mass. The acceleration is simply something to do with the force of gravity. Right? So the force of gravity depends on the mass, but not the acceleration. Yes.
So like with like no air resistance, like in a vacuum, does that like so any object would fall at the same
Acceleration.
And so does that mean like if you drop them like from the same height, they just both hit the ground at the same time?
Same time.
Okay.
So if you take a bowling ball and a ping pong ball and drop it from the top of the building, both will come down together. It's kind of unbelievable, right? Because that's only if there's no air resistance. Now, because of air resistance, the bowling ball takes the lead and then the ping pong ball kind of slows down. Or imagine a beach ball. A beach ball and a bowling ball, they look exactly similar, but one is heavier than the other. You drop it from the top, the beach ball, of course, is going to take its own time, and the bowling ball will come down fast. Whereas if it is evacuated, they both come together. I think there's an experiment. I recently saw a video that they made demonstrating the same thing, but on a massive scale. On a massive scale, like it's not a cylinder like this. But I don't understand why they have to spend millions and millions to do this experiment on a massive scale. Massive scale means what? I'm talking about 3-4 floor high, a big kind of a gymnasium kind of thing, huge hall. And then they've got big, strong doors, and it's all airtight and sealed and stuff like that. Very strong. All the walls are strong. It's kind of steel structure because you're going to evacuate inside. You're going to remove all the air from inside. So it has to, the wall cannot collapse, should not collapse. So the whole structure is very strong. And then after that, all they're dropping is a lead ball and a feather. It's the same thing. You can do that on in a cylinder and then demonstrate that effect. But then they spend so many millions just to demonstrate this, and cameras, slow motion cameras and everything attached inside, and then they are outside and they close the big door, seal, and after that they start the evacuation process. And once it's evacuated, then they release it by some mechanism, and then you can see them both coming down, hitting same time. It's interesting to see that video. I think you should be able to see it on YouTube. You should be able to see it on YouTube. Just check if you have a device, you can just check it up right now, in case.
Yes.
Your tire's just going.
Now, imagine you were not that bad a driver.
That's highly debatable.
Imagine you're not that bad a driver and you're driving decently at 45 miles per hour. You're just driving at the right speed. You are driving at 45 miles per hour now. Find where you will end up stopping if you hit the brakes and slam it. So you're going to do exactly the same procedure. What is this? 45 miles per hour. How do you convert meters per second? First multiplied by, and then divided by 3.6. How much is it? 20? So we have 20 meters per second. So now what will be the difference here? Acceleration is exactly the same, no difference here. Acceleration depends on the coefficient of friction. That's it. So if the grip on the road is not good, then you're not going to decelerate enough. So this is a very serious thing. That's why a wet road and a dry road makes a huge difference to your stopping distance. Okay, so if you intend to stop somewhere on a wet road, always calculate too much. So if you have the habit of moving your car behind somebody else's car just like that, keeping a very short distance, you have to maintain much more distance on a wet road. You can't just go back to back. Initial velocity 20, final velocity 0, displacement what? Acceleration negative 7.84. What is the displacement? Calculate. Where do you stop? When you're driving at 77 miles per hour, you stopped 75 meters away. Yes.
25.5 meters away.
25.5 meters away. You stop here. You see the difference? Every little increase in your velocity makes terrible changes to your stopping distance. Stopping distance drastically changes. You'll see how we calculate. 25 meters. That's not bad. 25 meters is like short distance. What if you are going only at 25 miles per hour? If you're going at only 25 miles per hour, check the difference. If you're going at 25 miles per hour, what will be the equivalent of it? 11.1 meters per second. Now go back here and put 11.1 and find out how far. Substitute and tell me how far you go. X equal to 7.9 meters. You know what is a meter? This is a meter. 7.9 meters is pretty much this much. So you are able to stop in such a short distance. So speed makes a huge impact on your stopping distance, and of course this one, depending on the road conditions. Now, if the road is perfectly okay, and imagine a sand truck kind of spills some sand on the road, road conditions are different now. You're not ready for it because you think the road is normal, because you've been going on the road multiple times, and that particular day you thought the road was normal, but a sand truck has spread sand on the road, and you were not ready for it. So you hit the brakes, and it kept gliding because this coefficient of friction changed. So if this coefficient of friction changes, that will change the deceleration. Deceleration is important for you to stop earlier. So if the coefficient of friction drops to 0.4, then the deceleration is going to drop to half of this. And then that is going to be severely affected. Questions?